Let's talk about g-forces on a ride. I guess the zeroth concept is that this object is going around and around, right? So its velocity is continually changing. It's got an acceleration that we call a centripetal acceleration, yeah? Okay, so at this point it's actually accelerating toward the center. It's accelerating right here. It's accelerating straight up. Here it's accelerating straight to the left. And at the top, if you're going to, can you picture this arrow there? It's accelerating down. Okay, so we're always accelerating toward the center. Okay, now the other thing to think about is that this ride is on Earth. This is a vertical circle on Earth. Okay, and so in this vertical circle, there's already 1g of acceleration, right? Okay, and so the ride sort of superimposes its g-force on top of that. Okay, so at the top, notice that we're accelerating down. So this is a negative acceleration. We're actually accelerating downward, just like an elevator accelerating down, only we're not actually moving that way, right? At the bottom, we're accelerating up. Okay, when I say 1g, by the way, I mean the acceleration of 9.8 meters per second squared, right? Okay. So 1g is 9.8, 2g's is 19.6, etc., right? Okay. Now, as the ride is accelerating like this, right, at the top, since you're accelerating down, you actually feel Earth's gravity, but you feel a little bit lighter because of the ride, because you're accelerating down, because you're accelerating toward the center. Okay, and the center is below you. At the bottom, you feel a little bit heavier by the ride's g-force, right, because you're accelerating up. Just like when you're on the elevator. When the elevator accelerates down, you feel lighter, right? So you feel lighter. Here you feel heavier. Okay, this is kind of a cool thing. We can actually measure this at Oaks Park. We'll make devices that can do it. You can do it with your phone, and we've got data for this. Okay, this is really pretty cool. So let's look at some of the slides here. This is the g-force on the Ferris wheel, right? So remember, you're heavy at the bottom and light at the top. So this is where we're at the top, right? And then this is where we're at the bottom. Okay. Now we can science. Matt Damon's character said in The Martian, we can science the heck out of this. So this is basically, oops, I got that a little bit low, but let's say that that's 1g. Now look, here's 10 meters per second squared, right? G is 9.8 meters per second squared, right? So it's a little bit less than 10 is the middle of that, right? And I imagine this distance to maybe be 0.1 g. I really don't know. We could analyze this, right? Okay. So at the bottom, it's 1g plus 0.1 or 1.1 g's. Just maybe it looks like 1.1. I'm just guessing. Okay. And at the top, it's 1g minus 0.1, so it's 0.9 g's. Yeah. Okay. So that's super cool. We can actually measure that. You wouldn't think a Ferris wheel is a thrill ride, but you can actually. There's a g-force, and I can actually feel that. Let's look at a somewhat more violent ride. This is the Rocco plane. The Rocco plane. A ride I've never ridden in all my years. Someday I should ride this, okay? Now, let's look at this. This is 1G right there, okay? And then look at this. This looks to be about 0.6 Gs, doesn't it? 0.6 Gs this way, right? And then this way is also about 0.6 Gs, right? So here we are at the bottom. The Rocco plane looks to be about 6 Gs, so it's 1G plus 0.6 Gs, right? Or, you know, there you go, right? About 16 meters per second squared, roughly, right? 1.6 Gs. And here it's 1G minus 0.6, or about 0.4 Gs. And this is at the top, okay? That's kind of fun, right? And we can actually also figure out what the period of this thing is, because we can measure the time. This is time in seconds, so we can. Anyway, I'm getting too excited about data from Oaks Park. This is the 0 G. This is a little more complex, right? But look at this thing, right? This is a and we'll talk about this later. This is a little more complex, but I just wanted you to see this, right? So this is where we're at the bottom. This is where we're at the top, okay? And this is a ride that actually inverts you, so it's a little more complex. You're actually facing this way, right? Here, it pins you to the outside of it like a washing machine drum and flips up on its side, and you look down across 30 feet of space, and the only thing holding you there is your inertia. And there's like a little safety belt or something like that that probably wouldn't save you. But anyway, yeah. All right, I think that's all the words I need to say about this.